Welcome to the 22nd lecture of combinatorics. In the last class we were discussing one of the interesting applications of inclusion exclusion principle, namely finding a formula for the Euler phi function in terms of the prime factors of n, the given number n. We suppose n equal to p1 to the power e1, p2 to the power e2. This is the prime decomposition of n. Suppose e3 and say pt to the power et. So we want to prove the following formula: phi of n is equal to n into product of 1 minus 1 by pi. I ranges from 1 to t. This is what we want. We have verified it in the case of prime numbers and like some of the smaller numbers. So now how do you get a how do you prove this thing? How do you derive this formula? So we want to do it using the inclusion exclusion principle. So for that purpose we define certain properties h1, h2 up to hk, ht, which see this h1, h2, ht are the undesirable properties, right? So which we don't want, because we are looking for numbers. When we count phi of n, when we want to figure out the value of phi of n, which all numbers from 1 to n in the universe is, see this n minus 1, right, 1 to n minus 1, which all numbers are such that they do not have any common factor with n other than 1, I mean relatively prime to n. That is what we are looking for. So when there is a common factor, that is not desirable, right? So therefore, so suppose there is a common factor, then there should be a prime common factor. If there is a common factor, there should be prime common factor also, either p1 or p2 or pt should be common to k and say n, right? So k, if we are analyzing k. So let us say we define h1 of k, right, h2 of k, ht of k for k in the range 1 to n minus 1, so that h1 of k says p1 divides k. Of course p1 divides n also. P1 will be a common factor between n and k, right? So therefore this is not a, this k would not be a good number, because if this property is satisfied by k, then p1 divides k. Of course n being p1 to the power e1 into p2 to the power e2 into pt to the power et, p1 will be a factor of n also. Therefore p1 is a common factor. Therefore p1 is k is not relatively prime to n. So this is not the kind of things we want, right? We want to avoid k which satisfy h1. So this is the first undesirable property. The second property we want to avoid is p2 divides k. Similarly then hi of k would be pi divides k. Similarly the last one pt divides k. So correspondingly we can also define the set a1, a2 and at as subsets of the universe, universe being this one n, right, universe being n 1 to n minus 1, right. So that's ai would mean ai is the set of numbers from the universe such that those numbers satisfy property, right. So hi of k is true, right, is satisfied as usual. Now it is very clear that what we are looking for is the cardinality of a1 complement intersection A2 complement intersection A3 complement intersection AK complement, sorry, AT complement. Why? Because you know this A1 means of course P1 is a common factor between the numbers of A1 and N. So A1 bar will not have P1 as common factor, A2 bar will not have P2 as common factor. I mean the numbers in A2 bar will not have P2 as common factor with N. So actually the numbers in A2 bar will not have P2 as a factor in it. Similarly, numbers in A1 bar will not have P1 as a factor in it. Numbers in A3 bar will not have P3 as a factor in it. And then number in AT bar will not have, AT complement will not have PT as a factor in it. So when you take the intersection of all these things, we get the numbers which do not have P1, P2, P3 or PT, any of them as a factor in them. So such numbers cannot have a common factor with N, because if at all you have a common factor with N, there should be a prime common factor, and these are the only primes which are in N, and therefore if these primes are missing in K, then this K has to be relatively prime to N, and this is the only way K can be relatively prime to N, because even any of these PI's are is a divisor of K, then there is that PI is a common factor. And then we can apply the inclusion exclusion principle here. We know how to use it. The value will be cardinality of U, right, minus sigma cardinality of AI, right, plus sigma for every I and j AI intersection AJ, right, AI intersection AJ if you take, and minus sigma IJK if you take AI intersection AJ intersection AK, right, and so on, right. Finally, it's minus 1 raised to T, right, the last one, right, AI A1 intersection to AT. This is what we should, right, estimate. This will be the answer, and this is what the cardinality of U is N, and this is the second term is, you know, for instance, when P1 is not a factor, how will I find? Suppose P1 is a factor, the numbers I have to consider numbers from 1 to n minus 1, and then how many numbers have P1 as a factor? We know that is n by P1. Okay, because we are minusing from numbers from here, because I think I was telling n minus 1. So this has to be n, because we have to, because we considered the universe now as n here for right. We can do it in n minus 1 also, but it is more convenient to consider the universe as n. So I'll change it. So here the universe let us take as n, right. As I told you, as far as the numbers which do not have a factor, or I mean common factor with n, that means the relatively prime number, whether you take up to n minus 1 or n, it does not matter, because you know n will not be relatively prime to n. But on the other hand, when we define these properties, the problem is that we are saying P1 divides K. Now it depends on whether if you take the universe as n will be definitely there in this set, right, and if you do not take n, then n will not be there. So but it is more convenient to take n as the universe, so that later the manipulations will be easier. So we will consider n, that means 1 to n as the universe, so that now when I wrote this thing, AI is equal to k element of n, Jk is satisfied. So this is n, correct, not n minus 1. So right, so right, so we take the universe cardinality as n, not n minus 1, right, because we are including n also in the universe, right. So I repeat, if you are interested in the number of the numbers from 1 to n which are relatively prime to n. So, we could in a sense we only have to consider numbers from 1 to 3 up to n minus 1, because n is anyway not going to be part of this collection. But the difficulty here is that we are actually defining this undesirable properties, right. So, then P1 divides k and trying to see how many numbers are satisfying that properties. So, there it makes a little difference, because if you define the universe up to 1 to n minus 1 only, so then n cannot be in this set. So, that will change the numbers, it will make the manipulation more complicated. So, therefore, we define u as n, so that n also will be in each of these AIs, right. So, that is what this will be taken as n now, right. This will be taken as n, and then sigma, the next one as you see up to n. So, we have how many numbers are divisible by P1 here. So, as we have seen before, it is n by P1, right. For instance, how many numbers from 1 to 10 are divisible by 2, you just have to take 10 by 5, right. Not that n by P1 is an integer, it is not a fraction, because n, if you remember, is P1 raised to E1 into P2 raised to E2 into Pt raised to Et. So, therefore, when you divide by P1 you will get an integer P1, P1 divides n, right. So, this P1 we will get a correct number, like here 10 by 2 is 5, right. For instance, if you had taken 11 and asked the question, you should have taken 11 by 2 floor, right. But in this case we do not have to do that, because P1 divides n. So, we say that for each Pi, n by Pi is the number of numbers divisible from 1 to n, which is divisible by Pi. So, this is from I equal to 1 to t for each of them, right. So, we have written this sum. For AI, the value is n by Pi. So, we just wrote it like this, right. Okay. So, now what we do is, you look at the second term is this one. So, if you take any two I and j, so what is the intersection cardinality? AI intersection AJ, right. To find this thing, what we can do is, so that means the numbers which satisfy both the property Pi and the property Pj, that is what we are talking about, right. So, but property Hi and Hj. So, if what does it mean to say that the property Pi is satisfied? It means it is the number is divisible by prime Pi, right. So, there will be n by Pi of them, and similarly there will be n by Pi numbers which are n by Pi numbers which are n by Pj numbers which are divisible by Pj. But when you say the numbers which are divisible both by Pi and Pj, divisible both by Pi and Pj, how will you find out? Because Pi and Pj both divides means Pi Pj divides it, Pj divides it, divides k, right. If a number k is divisible by both Pi and Pj, because this Pi and Pj both are prime numbers, if both of them divides k, Pi into Pj has to divide, and that is the only way it can divide it, right. So, it is clear that in number is divisible by Pi into Pj, then both Pi and Pj divides, and also if Pi and Pj both divides, then Pi Pj has to divide. So, instead of asking for the numbers which are divisible by both by Pi and Pj, we can ask for the numbers which are divisible by Pi into Pj. So, this number is Pi n by Pi into Pj. As we saw before, this is an integer because n has both Pi and Pj as factors. So, when you divide n by Pi into Pj, we will definitely get an integer. So, the next term here will come sigma for every ij, we will get every pair ij from 1 to t. So we can write n by pi into pj here, right. And next term would be similarly n by pi into pj into pk for I, j, k, right, because we now want the all the three properties hi, hj and hk should be satisfied for selected I, j, k. We are selecting any three properties hi, hj and hk, and then we want to count the numbers which satisfy from the universe, right, 1 to n, the numbers from 1 to n which satisfy all the three properties simultaneously, right. That means that those numbers should be divisible by pi, those numbers should be divisible by pj and pk. So, which is equivalent to asking for the numbers which are divisible by pi into pj into k, that is definitely n by pi into pj into k, right. This is what we will get. So, like this we can get a formula minus 1 raised to t. So, n by pi into pj into pt, this is what we will get, right. And so this formula, so this is the formula we will get when we substitute the values for all these terms here, here, here and all of these terms, right. This is what we will get. Now we can try to do a little bit of simplification here. What we do is we take n out, and then we get 1 minus sigma 1 by pi, right, for every I equal to 1 to t, and then this is sigma for every I and j in 1 and t, in the range 1 and t, we are taking 1 by pi into pj, and minus sigma for every I, j, k. So, we are taking 1 by pi into pj into pk, like this, right. The final term being minus 1 raised to t, 1 by p1 into p2 into up to pt, right. So, now what we can do now is we will divide it by p1 into p2 into pt, and then of course you have to multiply. If you divide it by this, then here you have to, in the numerator you have to multiply by p1 into p2 into pt, right. Every term should be multiplied. Then what we get is n by p1 into p2 into pt, and then first term will be p1 p2 pt, right. Second term will be some terms of this form p1 will be omitted first, p2 p3, maybe I can write it fully. So what we can do is, yeah, first p2 p3 up to pk. So what happens is here we have 1 by p1, then you multiply by p1 into p2 into pt, that one p1 will go away, all the p2 to pt will remain, and then next, so these are all inside one sum, right. Then p1 p2 will go, but p1 p3 p4 up to p this is t, right, pt will remain, and so on. Similarly, p1 to pt minus 1 will remain here, and so on, and plus now the next term would be of the form, because there are terms pi and pj's, right. Then other than say pi and pj, for every pi pj selected, all the other terms will remain here, say p1 up to pi minus 1, then pi will be missing, pi plus 1, and then up to pj minus 1, so pj plus 1 and then pt, this kind of terms will come in that. So like that we can enumerate all the terms, right. In the last term will be just 1, because that was 1 by p1 minus 1 raised to, sorry, we have a negative or positive term, minus 1 raised to t into 1, right. So this is what. Now if you carefully look at it, right, so see, it would be, for instance, if the student is finding it difficult to understand this thing, what is advisable is to take the case of say t equal to 3 and try writing all the terms, then it would be clear. So, because I have already spent a lot of time in this inclusion exclusion principle, I am not spending time to take an example and write it, but it is very easy for the student to try it out. So, but it is not difficult, and the next important step is this thing. So, see what we have achieved now is that this kind of here everything see 1 by form fractions were available here. Now, by multiplying by P1 into P2 into Pt all over, and what we have made is in the numerator we have only integer values. Now, fractions are all removed, but then this is familiar because if you carefully look at it. So, of course, you have to notice that if it's just discard it for the time being, just look at what is inside here, right. That is this stuff 1 by P1 sorry 1 by sorry this is P1 minus 1 into P2 minus 1 into Pt minus 1. If you expand this thing, what we will get is the first term will be P1 into P2 into Pt, right. Why here also we have P1 into Pt. What is happening is we are taking P1 from here, P2 from here, Pt from here, and then we will leave out what we will do is we will take 1 minus 1 from any of you. Remember how we proved the binomial theorem and all. So, we will take P1 Pi's from each of the terms except 1. From that 1 we will take a minus 1. So, therefore, the sign will be minus 1, but all others of this form, right, P2 for instance when I take minus 1 from this thing, P2 P3 Pt from here I will get minus P2 P3 up to Pt, right. Or if I take P1 from here and only minus 1 from here and P1 P2 P3 to Pt, then that is a minus P1 P3 Pt, right. Like that we can formulate all the forms, right. So, now finally, so the next type of things is when I take 2 minus 1s and rest all Pi's. For instance, I select from any of the 2 positions 2 minus 1s and then collect all the other Pi's. So, we will leave out 2 Pi, say so that Pi and Pj we divided off, right. That will correspond to minus 1 into minus 1, which is a plus, right. So, like that. So, this essentially the upper whatever we see in the upper part is nothing but this P1 minus 1 into P2 minus 1 into all the way to Pt minus 1. So, we can substitute it there like this n by P1 P2 up to Pt into 1 by P1 minus 1 into P2 minus 1 all the way to Pt minus 1. Now, you divide this by this, right. So, what we can do now is we take n out, this is equal to n into, so we will write it as a product n into, this is P1 minus 1 divided by P1, right. So, maybe you can instead of writing the product we will write like this, and this is P2 minus 1 divided by P2 and then P3 minus 1 divided by P3 and so on up to Pt minus 1 divided by Pt. This is n into 1 minus 1 by P1 into 1 minus 1 by P2 into, so 1 minus 1 by Pt. This is what we get. So, this is actually product of I equal to 1 to t 1 minus 1 by Pi as promised. The last two steps are only manipulation. So, we have just rearranged this terms that for below Pi minus 1 we wrote Pi, that is all. So, because below also there is a product, above also there is a product, we can arrange them properly. So, it is just rewriting it, and then Pi minus 1 by Pi is rewritten as 1 minus 1 by pi, that is all, right. The crucial steps are here noticing that what we see in the upper part in the numerator other than this, right, is can actually be expressed like this, because this is that was the expansion of this form. This people may miss, but you have to observe that, right. And then the earlier one, this one by multiplying, these are all usual steps, right. I mean, to get rid of the fractions, we multiplied by all the things which have appeared in the denominator, right, the common LCM of what we see in the denominator, the numbers which we see in the denominator, and got rid of all the fractions, right. So, that is what we did, right. Before that, it was the application of the inclusion. Just only thing is estimating the sizes of those intersection, the intersection of several sets. So, this is the way we prove this inclusion exclusion principle gave us this formula finally. Okay, we will move over to the next one, and here is another question. The 6 married couple are to be seated at a circular table. In how many ways can they arrange themselves so that no wife sits next to her husband? So, we will so 6 married couple are to be seated at a circular table. It is a typical question we were looking at, and there are 12 people then, right. So, how many ways they can they arrange themselves so that no wife sits next to her husband? So, we had discussed the circular arrangement problem very elaborately when we learned the division principle. So, we know that n people can be arranged around a circular table in n minus 1 factorial ways. Here what we say is that 1, 2, 3, this kind of, if you rotate them in, say, in one direction, right, either clockwise or counterclockwise, it is still the same, right, it is considered the same. So, not that if you write 1, 2, 3, 4, 5, this is not the same as writing, say, 1, 2, 3, 4, 5. But on the other hand, you can rotate either in the clockwise direction or in the counterclockwise direction, that is same. We had defined it as always we see the same left neighbor and the right neighbor, right, same neighbors won't change. So, neighbors, no, it is not neighbors won't change, it is that if you have a notion of left neighbor, because the clockwise neighbor, counterclockwise neighbor, they are not going to change, that is what we mean, right. So, of course, we can go back to that discussion once again if you have any confusion about the problem. So, that is, so we are referring to the same kind of arrangements. So, here we have 12 people, just that they are 6 married couple, 6 into 2, right, and the universe is all possible arrangements, as we say 11 factorial arrangements, right. This is the universe U. Now, the properties we want to avoid, the first property P1 will be that the first couple, we can say couple 1, couple 2, couple 3, couple 1 sits nearby, I mean consecutive position, so adjacent, sits adjacent, right. But in how many ways we can, I mean how many of these members elements from the universe, right, the arrangements from the universe will belong to this category, namely, so we can call A1 as the subset of the universe, the arrangements which satisfy property 1, namely the first couple sits adjacent. We know the technique to count that, namely say the couple 1, so the husband 1 and wife 1, say we will just tie them together, say that means we will introduce some H dash notation for that. So, some combined they will consider them as one person, and then we will arrange the resulting 11 persons around the circular table, that will result in 10 factorial arrangements, right, because 11 minus 1. But now wherever we see this special symbol, right, so let us say we call H dash, H1, right. So, then we will replace this couple there, but then this couple can be placed there either as H1 W1 or as W1 H1, right. There are two possible ways we can. So, as if we are reading from in the clockwise direction. So, in the around the table we are going in the clockwise direction. We can first place H1 and W F1, W after that, or first the wife and then husband, right. So, therefore, 2 into 10 factorial possible ways to arrange them, right. So, now we see that there are 6 couples we can select, 6 choose 1 couples we can select, right. So, there are how many properties? So, P2, P6, right. There are 6 properties, any properties can cause this thing. So, we say that this is 11 factorial is the universe size minus that sigma cardinality of AIs will correspond to 6 choose 1 into 6 choose 1 into 2 into 10 factorial, because those property this here this is that the special case that if you consider a set AI, its cardinality does not depend on which set it is only depend on. So, we are talking about so the case where A1 is equal to A2 is equal to A6, because you know which couple is sitting next to next is unimportant, because that count will be still 2 into 10 factorial, right. This is that case where we simplified, right. We gave a formula saying that so when in the situation that the cardinality of a collection of sets, say T sets selected from the K sets, right. If their intersection cardinality is always the same, then we can use a special formula, namely first the universe size is written as alpha 0 minus K choose 1 into alpha 1 plus K choose 2 into alpha 2, that formula we remember. So, this will come in that category. So, in the next case we are talking about two married couples are sitting next to next. So, whichever are the couples, two of them if they are sitting. So, what we do is we first replace say H1 W1 by H1, so by one symbol. So, H2 W2 by another symbol H2. Now, we have you know initially 12 people were there, now the 2 reduced, only 10. 10 people can be seated around 9 factorial ways, and wherever we see this H1 we will replace either by H1 W1 or W1 H1 in 2 possible ways. Here also H1 W1 or H2. So, 2 into 2 possible ways of replacing. So, 2 square into 9 factorial ways of replacing is there, right. So, therefore, this will correspond to 6 choose 2, any 2 couple can be selected, right, for that. So, 2 square into 9 factorial. The next term we can easily see is 6 choose 3 into, because any 3 couple are selected, and like this will become 8 factorial. Why? Because you know we are for each couple we are just replacing by one, each couple is replaced by one symbol now. So, from 12 3 will reduce. So, there will be 9 people, the circular arrangement will be one more less. So, 9 people are arranged around a circular table in 8 factorial ways, right. So, now this 8 factorial, after getting this, for each of the special symbols we have 2 ways of placing the husband and wife, either husband earlier, wife later, or wife earlier, husband later, right. So, therefore, 2 to the power 3 into 8 factorial possible ways of doing it, and 6 choose 3 ways of selecting the 3 couples, right, because yeah. So, there are 3 sets that I, j, k from 1 to k can be selected in so of case k choose 3 ways. So, this was minus, and then next is plus. So, that would be 6 choose 4 into 2 to the power 4 into 7 factorial. So, the student can easily figure out what is happening here. 6 choose 5 into 2 to the power 5 into 6 factorial, and next one, the last one will be 6 choose 6 into 2 to the power 6 into all the couple are sitting next to next, and then here it is 5 factorial, right. So, 5 factorial 2 to the power 6 ways. So, this would be the answer, right. So, of course, this is just a direct application of thing. What you have to understand to remember is only the number of ways of arranging n people around a circular table, that is n minus 1 factorial. And then here once the properties that we want to avoid is written out, then finding this cardinalities are easy, because you know a couple is now replaced by one symbol, one representative symbol, and then now the number of people reduces because of that, and then we know the circular arrangements accordingly. And then only thing is really this couple can sit in two different ways. Any couple, now it is only one symbol. When you replace the couple back there are two ways of replacing back, right. So, therefore, if there are some T couples we have converted to like combined or maybe represented by symbols, then each symbol has two ways of being right replaced back by the couple, right. Therefore, 2 to the power t will come there, that is the only thing, right. So, that is simple, this is simple. So, therefore, there is nothing, I do not think there are many new ideas in that, right. So, now the next question we can consider. So, here is a graph problem. In a certain area of the countryside are 5 villages. An engineer is to devise a system of two-way roads, so that after the system is completed, no village will be isolated. In how many ways can he do this thing, right. So, here of course, this is a question about graphs, because there are 5 villages I will place here. So, some 5 villages. Now, what we two-way road means just an edge. So, yes, if you are drawing a undirected graph on undirected edge, means you can go this way or this way. It is not like direction is not important here. And then yeah, we want to draw these edges, these are the roads, right. But the only condition is saying that it should not happen that no road goes to this village. So, we are creating a graph here, but making sure that there are no isolated vertices, that is the word, isolated vertices. Isolated vertices means the degree of the vertex in the graph is 0, right. Not that we are not talking about connected graphs here, while of course, this is indeed a valid way to assign the roads, right, or even this is a valid way to assign the roads, but this is not a valid way. So, how much ever roads you put here, this is not a valid way, right. Now, because there was an isolated vertex here, this we do not want, but not that this is valid. See, you can always have this kind of a system. So, though there is no connectivity here, for instance, from here we cannot reach here, but still as far as each village is concerned, they are not isolated. There is a road between two villages nearby. So, therefore, they are not isolated, right. So, this is valid. Similarly, yeah, so yeah, correct, this is also valid. So, this kind of things are okay, right. So, we just want to avoid isolated vertices. Now, how many ways you can do it? It is a matter of counting. Say the first, suppose if you do not have any restriction, it is just a question of how many graphs can be drawn, are there, graphs are there on 5 vertices is what you are asking, if the condition, the no restriction was there, right. See, for instance, note that we are talking about simple graphs in the sense that there are no loops, nothing like this. So, similarly, we do not put double roads here, right. So, it is only between any two villages we have one road, and then there is nothing like a village to the same village road kind of, okay, that does not make sense. in this problem at least. Okay, when we talk about graphs you should worry about it. There are no self loops, there are no multiple edges, multi edges, right. So, now how many graphs can be there? So, the it is just a question, it is a simple combinatorial problem. So, there are 5 vertices, how many edges are possible is what you should ask. So, the 5 vertices, how many edges are possible? Definitely there are 5 choose 2 edges possible, because any pair can actually define an edge. There can be an edge or may not be an edge, there can be or may not be an edge. How will you express this thing? So, there we can say that for instance, if there is an edge, so I will list down all these possible edges, right. So, for instance, this is say V1, V2, V3, V4, V5, right. So, now so the possible edges are V1, V2, V1, V3, say V1, V5, then V2, V3 up to V2, V4, and then we have V3, V4, V3, sorry, this is V5 and V3, V5, and then finally we have V4, V5, right. Total this many, this is actually 5 choose 2 is equal to 10, and yeah, this 4 plus 3 here, 2 here, and then 1 in the end, right. This is total 10 possible edges are there. Now, let us say this is the first edge, second edge, say fourth edge, this is the fifth edge, and like that we number the edges also, right. So, now we can decide whether the edge EI is present in the graph or not by saying whether it is 1 or 0, by associating with the 1. So, if you put a 1 for EI, then it is present, otherwise it is a 0. So, we have a binary string of length n choose 2 being defined, because we have a long string and the position ith position correspond to the ith edge the way we have defined, right, ith edge. So, if we decide to have that edge in the graph, then we put a 1 in that position, the string position, the ith position of the string, otherwise we will put a 0 there, right. 0 or 1 can be placed at the eith position, 0 or 1 can be placed in the eith position, 0 or 1 can be placed. Now, how many strings are possible? There are 2 to the power n choose 2 strings possible, because there are n choose 2 positions available. And you can see that any graph will correspond to a string this way, and if you on the contrary, the converse is that if you have any string, we can define a graph based on that. You just look at the ith position, if it is a 1, put an edge there, otherwise non put, right. So, what I mean is, if I get a binary string of length n choose 2, any binary string of length choose 2, I can get a unique graph from that on n vertices, right, in this way procedure. The converse is that if you get any graph on n vertices, we can write down the corresponding binary string. You just look at the ith edge, and if that edge is present, put 1 in the ith position, otherwise put 0 in the ith position, you get. So, therefore, it is same as counting how many binary strings are there of length n choose 2. So, that is 2 to the power n choose 2, right. So, in this case, if we do not have any restriction, n equal to 5, so n choose 2 is equal to 5 choose 2 is 10, right. There are 2 to the power 10 possible graphs. This will be the cardinality of our universe, all possible graphs without any restriction. Now, the properties that are to be avoided, P1 is that V1, vertex V1 is isolated. Similarly, P2 will be the property that vertex V2 is isolated. Similarly, P5 is the property that the vertex V5 is isolated. All these properties are undesirable because we do not want any vertex to be isolated. So, now we know what we are looking for. So, suppose A1 is the set of graphs which on 5 vertices which satisfy property B1, that means vertex V1 is isolated in that. Similarly, we let A2 be the set of graphs which satisfy property P2, that means the vertex V2 is isolated in the graph, and similarly A5. Now, we know we are looking for this set A1 complement intersection A2 complement intersection A5 complement. Why? Because we are looking for graphs on 5 vertices where the vertex V1 is not isolated and the vertex V2 is not isolated and the vertex V3 is not isolated and the vertex V4 is not isolated and the vertex V5 is not. This is just this intersection, right. And this we know, this is cardinality of U minus sigma AI cardinalities, right, for I equal to 1 to 5 plus sigma for every I and j, I pair ij, we had to find AI intersection aj and so on and so forth, right. A5. Now, how do we find the cardinality of A1? That is easy, because you know that the vertex V1 is not isolated. It is as good as asking how many graphs are possible on the vertex set V2, V3, V2, V3, V4 and V5. So, there are only 4 vertices, and then how many graphs are possible, because we are never going to put an edge incident on V1. So, it is same as asking how many graphs are there on 4 vertices, right. Discard one vertex. That is definitely 2 to the power 4 choose 2, namely 2 to the power 6, that is 2 to the power 6, right. And there is nothing special about vertex V1, that same counting is true for vertex V2, V3, V4, V5, anything. So, therefore, for each I equal to 1 to 5 we get this 2 to the power 6, right, 2 to the power 4 choose 2. Now, what about AI intersection AJ cardinality? This is also easy to find, because we want 2 vertices to be isolated simultaneously. So, for instance, V1 and V2 are to be isolated. Then it is as good as asking how many graphs are possible on the remaining vertices V3, V4, V5, right, that is what we are asking. And we know this is 2 to the power 3 choose 2, namely 2 to the power 3, which is 8. So, this is 8. And for every ij, it does not matter which 2 vertices we are leaving out, right. So, therefore, this is the same. And finally, if you want say AI the 3, same way we can find for when, for instance, when you take 3 vertices together has to simultaneously has to be isolated, that will end up as 2 to the power 2 choose 2, namely 2 to the power 1, right, because 3 vertices gone, and then how many graphs can be drawn on these 2 vertices. That is only 2 ways, either there is an edge here or no, right. And then finally, if 4 vertices are gone, there is only one way of doing it, that is 2 to the power 1 choose 2 is 2 to the power 0 is 1, right. So, we just have to, now we know how to find the cardinalities of all the intersection of all the required sets. So, we just use that simplified formula, I mean the formula which we derived for the simplified case, where the particular, I mean suppose T sets are taken and the intersection is made, and that cardinality only depends on T, does not depend on which T sets, right, that is this case belongs to that. Therefore, that would be this universe, cardinality of universe, namely 2 to the power 10 minus, right, if I choose 1 into 2 to the power 6 plus if I choose 2 into 2 to the power 3 and then minus if I choose 3 into 2 to the power 1, right, to choose 2 plus then if I choose 4 into 2 to the power 0 and then we do not have anything, right, because yeah, what the last one, for instance, when we say how many graphs are there with all 5 vertices isolated, that is like there is nothing. 0 choose 2 is what we are asking, that will be just 1 because you know there is a graph here with everything is isolated, there is a, so therefore that also will come, right, 2 choose 0. So finally that 5 choose 5 and that is, yeah, again just 1, the last one is just 1 because all the properties together are satisfied, all the 5 vertices are isolated, that means there is only one graph like that because isolated graph, right. So now what we do is the next one. So the next problem is about derangements. This is also an important problem. So we will quickly do this thing. Derangement means what? Suppose we have, so we are talking about permutations now, suppose 1, 2, 3, 4. So we consider the permutations of 1, 2, 3, 4. So we can always represent the permutation like this. So we first write the position, so 1, 2, 3, 4 here, and then maybe the permutation can be written below this 1, 2, 3, 4, say 3, 2, 1. Now we ask, at this first position do we get 1? No. The second position do we get 2? No. So in the third position do we get 3? No. In the fourth position do we get 4? No. Here every position we are getting a number different from the position numbers, right. So such a permutation is called a derangement of 1 to 2. So an example of derangement would be like this, say for instance 1, 2, 3, 4. So suppose if I take 2, 4, 3, 2. Here the first position we have no problem because it is not 1. The second position we have no problem because in the second position we are seeing 4 not 2. In the fourth position also we do not have a problem because in the fourth position we are seeing a 2 not 4. But in the third position we are seeing 3 itself. So this is something we want to avoid, right. This is something we want to avoid. So this is not a derangement. This problem can be right. There are usually we say that one situation we use to explain this derangement is, so say n gentlemen come to a party and they keep their hats on the table, and then while going back, each of them takes their hats back. He takes the hats back, takes one hat from the table. Now, the question is, in how many ways they can take back their hats such that nobody gets his own hat, right. He is taking a hat from the table, but there is no one among these n people who gets the same hat. So, that number of ways is the number of derangements, because their original hats are numbered by their, say, the person number 1, person number 2 up to person number n. The hats also has the number, say 1, 2, 3 up to n. Now, the person number 1 comes and takes a hat which is never 1, something else. So, when person number 2 comes and takes a hat which is something else, right. So, these numbers will be the whatever the person number 1, 2, 3 and takes, those hat numbers are written below them. Then in the ith position we will never see I, because if it is like that, then that means ith person has taken his own hat, right. So, in this situation we are asking for how many derangements are there, right, for the permutation 1 to n. Or in other words, another way to ask this question is, suppose there is a horse race and there are n horses, right. You can make a bet saying that, so the horses are numbered from 1 to n. So, you can say that the first, I can say first position, the first prize will be given, or the winner, the first place will be for horse number I can bet on that, right. And then second position will be horse number j, like that. So, if I can bet for each position, the first will be this, second will be this horse, third will be the one who finishes the race first, right, second, third, fourth, all the n horses. Suppose somebody puts a bet like that, essentially he is selecting a permutation of the horses, right. So, for the first his permutation pi of 1 correspond to, according to him, that horse will come first, right, and pi of 2 means according to him that particular horse will come second. Pi of I means the ith position will be obtained by that horse. Now, in how many permutations are there, how many ways you can lose all the bets? I mean, none of his bets are correct, means there is no I such that in the ith position the horse he predicted comes. So, this is in that case we are again counting the derangements. This problem we will discuss in the next class, and this will be the last in the inclusion exclusion thing.